Hello, in this video here we'll be looking at a diffraction resolution problem. Okay, now the problem is, imagine there's a car a long way and somebody's standing on a hill somewhere and they're looking at a car. Now a car has two headlamps. It's at night. I represent these as the headlamps. Now if they're a very long way away, the headlamps will appear as one headlamp, and as they get closer and closer, suddenly the person will make out two headlamps, and that's all down to due to the Rayleigh criteria and resolution that we discussed in the earlier video. So in other words, the closer it is, the easier it is to make out two sources of light. So what we're going to make is we'll have a person, and we can represent. First of all, I'm going to draw a line along here, just to give myself a centre. That wasn't a very good line. Now, let's say we have somebody with an eye, and let's say they can look it through their eye, take one eye, one pupil, and we're going to estimate the pupil to be, when the light comes in, to be 4 millimeters, and that is 4 times 10 to minus 3 meters. And the light is going to go from each point source through the slit, okay, and then it's going to hit at the back of the eye, the retina. So something like that. So what we'll find is that from here we'll get a point source. It will go through the slit, the eye rather, the pupil, go through there and hit the retina, and this one also will go through the middle there and hit the retina. Now we're going to call this angle here theta, and of course this angle here between them will also therefore be theta. Okay. Now imagine here and here we're going to have diffraction patterns because of light from here passing through a slit and here through a slit, and the Rayleigh criteria for them to be distinguished between each other is that the angle to the first minimum of one of them is going to be equal to this circular slit, it's 1.22 times the wavelength of the light divided by the slit width B. So this is B, as the slit width is the I here. These are the angles. Well, actually, that's theta. It's twice the angle of the first minimum. But we'll look at that at the maths. And this here is our point sources. Now let's put some distances on here. Let's put some values. So we've got B is equal to 4 times 10 to the minus 3 meters. Let's say the distance between the headlamps, let's make that 1.6 meters. So that is 1.6 meters. And the distance between the pupil and the light source, let's call that D. Here. So that distance there between there and there is D. So we're looking for what D is. What is D? How far will it be until, as the car is approaching, the person can just make out there's two headlights? So now, first of all, well, we find that angle there, theta, is the same as that angle there, theta. So we can then, by geometry, extrapolate it back. So now theta, if you go to theta over 2, what we find is that theta over 2, which is that bit there, or in fact the tan of theta over 2 is opposite over adjacent, is equal to half that, so that's 0.8 divided by D. Okay. Now then the next idea is from here. Now in radians, for small angles, tan of theta, and sine of theta, from that matter of fact, sine and tan of theta tends towards theta. So that there can be rewritten as theta over 2 is equal to 0.8 divided by d. Okay, because theta over 2 will be is there. Okay, and therefore what we'll find is that from there, in fact I'm going to give some more space. From there we'll find that theta is equal to 1.6 divided by d. So the angle we're looking for, theta there, is 1.6 over d, and of course we can then put it into this equation here where theta equals 1.2 lambda over b. So, make myself some space. So, here we go. Therefore, 1.6 over d is equal to 1.22 lambda divided by b. Now, the wavelength for light we're going to take as 500 nanometers. That will be the average wavelength. So we can put that value into there. And we have b is equal to 4 millimeters, 4 times 10 to minus 3. And we just want to find out what d is. So, we put those values, put lambda into there and b into there, and what we find out is the distance is equal to approximately 10.5 kilometers. And that's how we approach a problem like that.